Let's say 70. You have groups of 2 all around. Just got to have the chances that are so small. That's the only reason, honestly.
Okay, good morning everyone. Good morning. A couple of things. First is I have posted a new homework set. This is on all of radiative heat transfer that we've done so far. Those problems are slightly shorter. Okay, they're mostly an application of the formulas that we have seen. So this will be due next week, Tuesday, according to your due date on the syllabus. So this is homework 8, posted on carbon. Then you're going to have an exam next week. This will be along the same lines as midterm 1. This will be held over a span of 2 days. You'll have a 4-hour window. You choose a time that works for you, and you'll be having the exam posted on carbon. The exam will cover the following topics. This is exam 2. This will cover topics on fins. Then we will also have topics on transient conduction. And all of radiative heat transfer until what I teach on Friday. Okay? Plus radiation. Today is the 23rd, so 25th, right? Up to. And then the final exam typically is comprehensive, but it will be more heavily towards what we're going to cover right starting from this week, when we will do real radiation problems, radiation exchange between multiple surfaces and so on. So that's something that will be there. Convective heat transfer will be a part of your final exam as well. I hope to wrap up radiation in the next few lectures, three lectures or 4 lectures, and then move on to convection. And then we'll also talk about heat exchangers at the end of the semester. Yes, question?
Is the final going to be the same setup as exam 1 and 2?
Absolutely. The final exam is open only on one day. It's open on the last, the actual exam date that you're supposed to write it on. The setup is the exact same thing, 4 hours. I don't know, I gave 5 hours for the first exam. I gave 4. You want 3 or 4? 4 is fine. 4 is fine. So 4 hours. Maybe the final exam I'll give an extra hour, 5 hours, because it's a little more comprehensive. Convection is quite painful. So, okay, so the same setup as exam 1. I see a lot of love for heat transfer. Okay, so what I'm going to do today is we will use what I'm going to do today to revisit some assumptions that we made at the beginning of the semester. At the beginning of the semester, we said that we can have what are called as diffuse gray surfaces, for which the absorptivity is equal to the emissivity. So under what circumstances are these proved? Under what circumstances are these true? And how do we go about doing it? And if we do it, is that the end of all our problems? Probably not, but at least it's simplifying certain set of problems. Okay? And the idea that helps us sell this concept is Kirchhoff's laws of radiative heat transfer. Alright, so Kirchhoff's law, the same person who did seminal work on electrical circuits and so on, was also involved in lots of ideas in mechanics and in heat transfer. We are going to consider the following thought experiment, and one can also actually realize this in real practice. Okay? So I'm going to consider a very large cavity. This is a large cavity with a very small aperture. Probably somewhere here. Okay. And if you recall, at the beginning of radiative heat transfer, or one of those lectures at the introductory part, I mentioned that when we talk about ideal bodies, we can actually recreate an ideal body using a large cavity with an aperture. Which implies that if I have a ray of radiant energy entering through this aperture, that is going to have multiple reflections within the cavity. And as it undergoes multiple reflections, the photons are going to have a transfer of energy. And eventually, what will happen is that all the radiant energy that is present within the cavity is going to be diffuse. Which means all the radiant energy that is emitted by the walls of the cavity will be independent of direction, independent of wavelength, and a function solely of the temperature of the walls of the cavity. Okay, this is something that we have looked at the beginning of the introductory part of radiative transfer. I'll write this down. Okay, so, radiant energy enters cavity. It undergoes repeated reflections. Within cavity, multiple reflections. And what happens is it reaches a state that is called as a thermalized state, the cavity itself. Is thermalized, meaning the radiant energy emitted by the walls of the cavity is solely a function of the temperature of the walls of the cavity only. Okay, so this implies the radiation intensity from the walls of the cavity, radiation intensity that is emitted by the walls of the cavity is a function of the temperature of the cavity only. And such radiation is called diffuse because it's independent of the direction. And if by chance any of this radiant energy can escape through the aperture, then the aperture is going to emit in a diffuse manner as well. Okay, so the intensity of radiation emitted by the walls of the cavity is diffuse. And let's say that this cavity is an isothermal cavity, so maintained at the same temperature. Isothermal, and let's say that at some point in time the temperature of the walls of the cavity is T surrounding. Okay, so this is the temperature at the walls of the cavity. Now, I'm going to take a small object and place it within the cavity. And let's say that the surface temperature of this object is Ts. what's going to happen? That's essentially the question that we are asking ourselves. So the object is at a certain temperature Ts, surrounding is at a certain temperature T surrounding. If I let things go for a very long time, what's going to happen eventually is they will reach equilibrium. The temperature of the object will become the same as the temperature of the surrounding. And this is a very strict condition, and it's called as thermodynamic equilibrium. So eventually, the entire setup, the system and the surroundings, the system being the object, plus the surroundings, reach a very strong condition called thermodynamic equilibrium. Which I'm sure you will come across in thermodynamics. But here is the upshot. I'm ignoring all other modes of heat transfer here. There's no convection. Let's say that this is a perfect vacuum condition. There's no conduction, there's no convection, there's only radiative heat transfer. So in thermodynamic equilibrium for the system and the surrounding, the temperature of the surface is the same as the temperature of the surrounding. So that's the first thing. So Ts is equal to T surrounding, or TSUR. And the second thing is that the net heat flux on the surface is 0, on the surrounding is also 0. Okay, so that's thermodynamic equilibrium. Net heat flux is 0. This is strict thermodynamic equilibrium. And we operate under the following condition. We will say that the total emissivity of this object is epsilon, its total absorptivity is alpha. Okay, so let's say that to be the case. So epsilon alpha is the total absorptivity of the object, or I should strictly say surface, because we are not considering any volumetric effects here. We are operating under thermodynamic equilibrium, so this is thermodynamic equilibrium shorthand TE. Look at the object. What should be true? The net radiative heat flux should be 0, because that's the only mode of heat transfer taking place here. So Q double prime radiation is equal to 0 at thermodynamic equilibrium. Does this make sense to everybody so far? It is kind of hard to establish thermodynamic equilibrium because surfaces and surroundings are always not necessarily cognizant of each other's presence, and there could be participating media in between the surface and the surrounding, which will complicate the matter further. But let's assume that these are the conditions. This is the condition for Kirchhoff's law to hold true. Thermodynamic equilibrium, temperature of the surface is the same as the surrounding. Net flux is 0. If I go ahead and say net flux is 0, the flux that is emitted minus the flux that is absorbed, that's the net radiative flux, that's 0. So far, so good. The surface is not an ideal surface. The surface of the object is not an ideal surface, which means that its emissive flux or emissive power is a fraction of the emissive flux or the emissive power of an ideal body. So I can say E is epsilon times E suffix B, which is the temperature of the surface, G absorbed is a function of two things. It's a function of the surrounding medium. It depends on the radiation from the surrounding medium. It also is dependent on the absorptivity of the surface. So this is going to be alpha. This is G absorbed, alpha times G. But look at this. The surrounding is also a thermodynamic equilibrium. The surrounding, because of the fact that it is completely thermalized inside, it behaves as an ideal body. So all of the radiation that's coming out is equal to its emissive power, which is nothing but the emissive power of an ideal surface at the temperature of the surrounding. So I have E of the surrounding minus G absorbed of the surrounding is equal to 0, but this is an ideal surface, so epsilon is equal to 1 for the surrounding, alpha is equal to 1 for the surrounding. It's an ideal surface. Because of that thought experiment that we have, the cavity is thermalized, so alpha is equal to epsilon is equal to 1. Which means that G is nothing but E of the surrounding. And I want to make sure that equation makes sense to everybody. Let's reflect on that. Alpha is equal to 1, so G absorbed is alpha times G, but alpha is equal to 1, so G absorbed for the surroundings is the same as G surrounding, which is nothing but the emissive power from the surrounding, because the surrounding is also in thermodynamic equilibrium, and the net radiative flux is 0. And so this is nothing but the energy emitted by an ideal body, which is at the temperature of the surrounding. And so if I now use that result and bring it here and couple all of these things together, so from here, for the object, I have the following: epsilon times EB is equal to alpha times G, which is actually that of the surrounding. Right? This is the same thing as the radiation on the object. But G surrounding is EB, so this is alpha. But T surrounding is the same as Ts, because everything is in thermodynamic equilibrium. So I see that alpha is the same as epsilon. Does this make sense to everybody? Yes or no? Any questions at least? This is for the object, for the surface that you're talking about. These are the relationships for the surface. This is not equal to 1 because it's not an ideal surface. This is obviously not equal to 1 either. This is the emissive power of an ideal body which is at the same temperature as the surface. This is the irradiation G on the surface, but the surface is obtaining irradiation from the surroundings, so the G on the surface is the same as the G on the surroundings, but a fraction of that, alpha times G. And if I then say that, okay, they are all in thermodynamic equilibrium, so the temperature of the surface is equal to the temperature of the surrounding, then this character is the same as that character, so alpha is equal to epsilon. So under these very strict conditions of thermodynamic equilibrium, when you have a small body surrounded by a very large cavity or a very large surrounding, you can have alpha is equal to epsilon, which is no good for us because you are never going to realize thermodynamic equilibrium. It is very difficult to obtain that. So we have to come up with some saving graces, and here is the idea. So I'll first write out Kirchhoff's law. For thermodynamic equilibrium, with the surroundings acting as an ideal body, we have for the object that is placed within these surroundings, alpha is equal to epsilon. This is very restrictive. The reason why it is restrictive is there has to be thermodynamic equilibrium. Temperature of the surface same as the surrounding, net radiative flux is 0. Another restriction is that the surrounding has to act as an ideal body. I can take the same thought experiment and I can say, okay, hey, rather than look at the total emissivity and absorptivity, let us do this for one particular wavelength lambda, and I will end up with the same equality but with respect to a particular wavelength, or I can say that alpha lambda is equal to epsilon lambda under these conditions. Okay, so extend this analysis to a per wavelength basis. We will end up getting alpha lambda is equal to epsilon lambda. Same conditions. Thermodynamic equilibrium, surrounding acting as an ideal body, and it's no surprise if the total emissivity is equal to the total absorptivity, why can't these two be equal to each other? And then I can say, okay, hey, why just focus on a particular lambda, how about a particular direction? So for a particular wavelength and for a particular direction, if I extend the same thing, I will come back to the most basic equation. Extend analysis on a per wavelength and direction basis. We will end up having alpha lambda comma theta. Remember, spectral directional emissivity, the function of lambda theta and phi, but not much of a dependency on phi. Okay, this is equal to alpha epsilon lambda comma theta, lambda theta phi. All of these are valid for thermodynamic equilibrium. First restriction and second restriction. And these three are called Kirchhoff's laws, but the saving grace is the following. It has been found out from experiments that this lost equality here is true regardless of the conditions. So what has been seen is that from experimentation, alpha lambda comma theta, which is the spectral directional absorptivity, is equal to the spectral directional emissivity because they are purely properties of the surface only. And that's the interesting thing. So which means that even if I don't have the system and surroundings in thermodynamic equilibrium, even if my surroundings are not ideal, I am always going to have this equation to be true. And this is called as a local thermodynamic equilibrium, in the sense that there will be some energy states that may not necessarily align with the fact that the temperature of the surroundings and the object is not the same. Okay? So the least restrictive, or no restrictive, no restrictions, and this is experimental evidence, a good resource. There is actually, I can mention the book here. It's Radiative Heat Transfer by Siegel and Howell. So this is a book where they show the experimental details that go into proving that, okay, alpha lambda comma theta is equal to epsilon lambda comma theta. I think copies of this book are available in the library. It falls beyond the scope of what we're talking about to go through those details. But it suffices to say that without any restrictions, this is always true. So this is great, okay, but it still is kind of complicated, right, because this is a function of multiple things. So what we want to see is the following. Okay, you're telling me that alpha lambda theta is always equal to epsilon lambda theta. Will there be a slightly less restrictive situation when epsilon lambda is equal to alpha lambda? And under what condition, if it is not thermodynamic equilibrium and so on, under what conditions will it hold that alpha is the same as epsilon? Which is going to be more useful for our problems. We don't operate under thermodynamic equilibrium all the time. Our temperature of the surface is different from that of the surroundings, so under what conditions can I still have these nice relationships which I slid up, okay, for alpha is equal to epsilon and the other thing. And here is the answer, and I'm going to show it step by step. So always true, mostly true, sometimes true. What is always true is from experimental evidence, alpha lambda comma theta is equal to epsilon lambda comma theta. We just wrote it down multiple times. They are all functions of lambda, theta, weakly dependent on phi, so I will refrain from writing that. Under certain circumstances, it is mostly true that alpha lambda is equal to epsilon lambda. What are the conditions under which this is true? We are going to prove it now. This will be true under two conditions. If surface is diffuse or if the irradiation is diffuse. And we're going to show it, okay? What is sometimes true but mostly useful to us is epsilon is equal to alpha. And we're going to show, which is going to go back to the beginning of the semester, we're going to show that if my surface is diffuse and gray meaning the emissivities and absorptivities are independent of wavelength, then this is true. And we're going to look at the meaning of all of these things now. And of course, there's also one more condition under which this is true. We're going to see that too. Okay. So just to recap, the basic idea is, okay, you have Kirchhoff's laws. The great news is under the set of restrictive assumptions, I can show that alpha is equal to epsilon, alpha lambda is equal to epsilon lambda, and directional spectral quantities are also equal. Not much of a good for us because we don't operate under such restrictive cases, so we need to relax the constraints. And in doing so, we come up with the fact that experimental evidence beckons this to be always true. And the question that we are asking ourselves is, when is this true and when is this true? And are we going to have problems where we can make such assumptions? Which is where we are heading towards. Okay, so first one. When is alpha lambda is equal to epsilon lambda? We start off with the definition of each of them. So first of all, epsilon lambda. Remember, if your subscript is lambda, your integration is over all the directions. If your subscript is a direction, your integration is over all the wavelengths. So this is going to be integral 0 to pi by 2, 0 to 2 pi, lambda comma e, sine theta, cos theta, d theta, d phi, divided by that of an ideal body. This is integral 0 to pi by 2, 0 to 2 pi, lambda comma b, sine theta, cos theta, d theta, d phi. Okay, this is the basic definition of epsilon lambda. What I'm going to do is, I'm going to write I of lambda comma e in terms of epsilon lambda comma theta. Okay, so we also have, this is the other definition, epsilon lambda comma theta is equal to I lambda comma e divided by lambda comma b lambda theta phi. So I'm going to substitute for this guy from this expression here by cross multiply. Okay, so if I do the cross multiplication, then epsilon lambda is 0 to 2 pi, 0 to pi by 2, epsilon lambda theta, I lambda comma b, sine theta, cos theta, d theta, d phi, d theta, does not really matter, by the denominator, 0 to 2 pi, 0 to pi by 2, so far so good, right? All we are doing is just substitutions and making use of basic definitions and then performing the substitutions. Now, in this integral, can I cancel off any quantity? In this integral here, the top and the bottom, can I cancel off anything? I could do that, but within these quantities here, can I cancel off those two? Yes. Say that again. I could do that. If I do this, I could do that. I can't do that really because this could be a function of theta and phi. So I can't cancel off the sine and the cosine. I can cancel these off because they are not functions of theta and phi. They are for an ideal body. They are diffuse. Okay, so I can cancel those two fellows off, and then I end up with the nicer expression. Epsilon lambda is 0 to 2 pi, 0 to pi by 2, lambda theta, sine theta cos theta, d theta d phi, all of this by something similar. Okay, So I have those. I can't do anything beyond that, so let's put a big box around it and forget it for the time being. I do the same thing with absorptivity. And what's my intent? My intent is, okay, I have done this for emissivity, I do it for absorptivity, I compare the two and I say, okay, under what circumstance can they both be the same? Okay, so let's do this for absorptivity. By definition, alpha lambda comma theta, the function of lambda, theta and phi. This is similar to that ratio, but I have to look at the intensity of the incident radiation and the absorbed portion of that and the total incidence. Lambda comma I, absorbed, this is 1. Then alpha lambda, which is what I'm actually looking for, is double integral 0 to 2 pi by 2 lambda comma I comma absorbed sin theta cos theta d theta d phi. It's a lot of writing of these integrals, which I agree with is quite tiring for me. Sin theta, cos theta, d theta, d phi. It almost seems like an imposition, right? Writing these things again and again. But the good news is you might actually remember it if you write it multiple times. Some of us. Hopefully you. All right. Okay, now I'm going to do the same thing, substitute for I lambda comma I, absorb using epsilon alpha lambda comma theta. So take this creature, substitute from there. So I have alpha lambda is 0 to 2 pi, 0 to pi by 2. Now watch this. Alpha lambda comma theta is the same as epsilon lambda comma theta. I'm going to do that substitution now. So we are substituting alpha lambda comma theta is epsilon lambda comma theta. They are functions of lambda and theta and phi, of course. So I'm doing that substitution, so I'm not going to write alpha, I'm going to write epsilon. So this is now epsilon lambda comma theta. I lambda comma I sin theta cos theta d theta d phi, all of this divided by something that looks similar to it but without the epsilon. So two big expressions to compare. Can you tell me when will this expression be equal to this expression? We've done all the writing that we can do for the day, and while I hunt for a new chalk, can one of you tell me when will these two boxes be equal to each other? It doesn't equal 1 typically. any takers.
If it's ideal,
If what is ideal?
the surface
Which surface? Surface or surrounding?
or surrounding. Sorry.
So if the surrounding is ideal, then what happens is that this will become independent of theta, and so I can cancel this off with that, and obviously since this is the same as that, those two integrals are the same. So this means that the surrounding radiation is diffuse, or when the irradiation is diffuse. Alpha lambda is equal to epsilon lambda. So when, okay, I forget English sometimes. When irradiation is diffuse, then I lambda comma I lambda theta and phi is just that, right? And so in that case, I can say that epsilon lambda is equal to alpha lambda because this cancels off with that, and that's the same integral. Now, what's the second situation under which these can be equal? Look very closely. Can I play around with this integral and take out a certain quantity so that this ends up being the same as that big block there? What if I do the following? What if I take this creature out of the integral? When can I do that? I can do that if epsilon lambda comma theta is no longer a function of theta and phi. If that is going to be true, then I take this out of the integral. So this is now the same as that. This is just a constant that's coming out, which obviously is going to end up being the same situation here. I can take this creature out of the integral as well, and now I can cancel off the sine theta, cos theta, and all the numerator and the denominator. And so when the surface is diffuse, which means that alpha, lambda theta, and epsilon lambda theta are independent of theta and phi. That's the second case. That is alpha, lambda, comma theta, which is obviously the same as this guy, is independent of theta and phi, so I will not have these written inside. And so this is the condition. This is under which alpha lambda is equal to epsilon lambda, and now we have to go to the big thing. Okay, this is great, but this doesn't tell me that the total absorptivity is the same as the total emissivity, which is what I need to solve my problems in a nice, nifty manner. But this is still good news. At least a little bit of my pain has been eased when that happens. Okay? And you'll see how much when we solve the problem on Friday. All right. The next big question, when is epsilon is equal to alpha? I'm going to operate under the assumption that the following is true. My no restriction case, so we know this is always since the humidity in the room is a little high, so the surface is damp, little failure happens. I'm also going to operate under the assumption that alpha lambda is equal to epsilon lambda. Okay, so let us say which can be true when either A or B is true. So this big thing here is this is OR. I don't need to have both of them to be true. Please notice that. It's not very restrictive. It is still restrictive. It's not always true. But if I have a diffuse surface, then I don't need to go through any hoops. I just say epsilon lambda is equal to alpha lambda. Okay, so let us say this is the case. So either surface is diffuse or irradiation is diffuse. Then I want to prove, okay, when is epsilon lambda is equal to alpha lambda? So we'll write it out and then we'll look at it. So epsilon, by definition, is the following. It is integral 0 to infinity E of lambda d lambda E of lambda comma b d lambda. Do you guys have a question there?
No, sorry.
If you'd like to talk, you're welcome to move out. Alright, so epsilon is defined as the ratio of these two. And we can further say that epsilon lambda is E lambda comma B. Okay, these are relationships that we have written in the past, so I'm not going to go over it again. So instead of epsilon lambda, I'm going to substitute instead of E lambda, I'm going to substitute epsilon lambda times E of lambda comma B. Okay? So we have epsilon is 0 to infinity, epsilon lambda comma b d lambda, epsilon E of lambda comma b d lambda. And as I have mentioned multiple times, please do not cancel off the thing inside this integral with the integral on the top there. Okay, they are both functions of wavelength, and epsilon lambda could also be a function of wavelength. By the same stretch, we can write alpha as the following. So alpha lambda is g lambda absorbed by g lambda. This is something that we worked on in the previous lecture. We had a problem where we calculated alpha lambda using this. And alpha is integral 0 to infinity g lambda absorbed integral 0 to infinity g lambda d lambda.